Now we want to combine these ideas we have so far and put it all together in predicting neutralization products. So we want to be able to predict the products that will form from mixing each pair of reactants. So I have HNO3, that's nitric acid, plus hydroxide, HF, hydrofluoric acid, plus ammonia, and then ammonium plus hydroxide. And for each of these, I would like to know what the products are going to be. Okay, so we want to predict the products that will form from mixing each pair of reactants. And so I'm just given two sets of reactants in each of these cases, and I want to figure out which one, what I'm going to make. And so what I can kind of diagnose or look at here is that these are going to be acid-base reactions. And so these are going to be Brunstad-Lowry acid-base, where I'm going to be looking at transferring an H plus between my reactants. And so what I really want to do is kind of put together all the ideas we've looked at so far. What is the acid? What's the base going to be? And then how does that transfer look like? And so when I start my first case, I have HNO3 and OH minus. And I want to parse out what's my acid and what's my base. And when I'm looking at this, one of the things that I want to think about right away is that whenever I see OH minus, we know that that's kind of our hydroxide is our kind of standard molecule for bases and kind of description of base. So this is always going to be a base. OH minus is always going to be the base. You can see that the H is written in the front here of this molecule. That is indicating that it is an acid. And so we would expect that that's going to be HNO3 is going to be my acid, and OH minus is going to be my base. So HNO3 is going to be the acid. That means it's going to donate a hydrogen, an H plus. And so we know that the rest of this is going to stay the same. The NO3 is still going to be there. Okay, it's going to lose the H. There's only a single H, so it goes down to 0. I was neutrally charged. I go to -1, and that is aqueous. And so you'll note that what we've created, this right here, comes to right here. This is the conjugate base. All right, so the whole idea of predicting these conjugate pairs is because that's what the product will be in the reaction. So HNO3 becomes NO3 minus. You get a nitrate out of it. OH minus is functioning as a base, so it's going to gain another hydrogen, has 1, it's going to become 2. This is a case where we do rewrite it to be H2O. We do want to be careful. The phase on that is a liquid. That is one of the more common issues when you have an acid-base reactions. You go to write your phases, AQ, 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 AQ. Water is not dissolved in water. It just is the liquid. But you will note that going from OH to H2O, water is the conjugate acid of hydroxide. So we can continue. HF aqueous plus NH3 aqueous becomes what? When we're looking for these things, H in the front, usually a good sign of this thing being an acid. A nitrogen in the molecule tends to be a good sign of being a base, especially when it's written in the front like that and there's hydrogens. You'll note here the H was in front of the N because that was functioning as an acid. Again, we tend to write things with the H in the front when it's an acid, hence why like water has the H in front, but hydroxide gets rewritten, but the H is in the back to emphasize the fact that hydroxide is not an acid. We move the H into the back of the molecule. And so once we do this, once we designate that HF is going to be the acid and H3 is going to be the base, we can then expect, what's going to happen from there. Well, the HF is going to donate an H+, so you're going to be left with F- aqueous plus, this is the N is still going to be there. You have the H, but instead of having 3, you go to 4 plus aqueous. So one of the things that we can do to check or kind of, see what's going on, that the NH3 becomes NH4 plus is the conjugate acid. So that's a good sign. And F minus, if it came from the acid, the F minus is the conjugate base, which is a good sign if we're indicating that F minus, because that cannot have hydrogen, so that needs to be a base. So that is a good sign that we would call that our conjugate base. So now I got NH4 plus and OH minus. And so again, whenever I see OH minus, that has to be the base. That just straight up always is the base. This has to be the acid then. If one of your reactants is the base, the other one has to be the acid. You'll note there's a nitrogen in there. We kind of tend to think that that may be, nitrogens tend to be bases, like we've seen, but you'll note it's also a cation. It's a plus. So N's that are molecules containing nitrogens that are positive, those do tend to be acids because they're the conjugate acid of when the neutral thing acted as a base. So you can see it was the conjugate acid here. So that means it is capable of basically donating or reacting where it gives away one of those hydrogens, which it's going to do in this reaction here. And so as a result, you can also then see that if this thing functions as an acid, it's going to still have the N, but it's going to lose one of its hydrogens, become NH3, and then it's going to lose its positive charge, making it just neutral, NH3 aqueous, and that becomes the conjugate base, which we saw up here. It's the same pair that we had previously, right? NH3 and NH4 plus, because these were on the reactant side, they didn't have the conjugate in front of them. But you'll note NH3 is always the base, NH4 is always the acid in this conjugate pair that we're dealing with. And so NH3 is the conjugate base, so OH minus is acting as a base, hydroxide is acting as a base. We've already seen it goes to H2O, and again, and that would be the conjugate acid. So that's the beauty of acid-base chemistry, because it's this small change that is a predictable change. You're just moving an H+. You can take your reactants and predict what the product will always be.
Participation 10.7, question 2. Predict the products for the following reactions. A, NH3 aqueous plus H2O liquid becomes what? And B, CH3COOH aqueous plus H2O liquid becomes what? This is the second question on participation 10.7, due Tuesday, October 7th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, predict the products for the following reactions. It's NH3 and H2O, and then CH3COH and H2O. I'm just going to write out the chemical formulas of the products is what I'm looking for. You don't necessarily need to write everything or give them names. Just chemical formulas of the products.
So bringing us to an important question of why do we care? Why do we define all of this idea of acid-base chemistry and see what we can do? And one of the main reasons is actually all of what we've talked about so far. The fact that these are small, simple changes that we can predict the products for. So if we can predict the products of a change, that allows us to strategically cause chemical changes. And one of the really important things about acid-base chemistry is that the transfer of H+ is an small elementary step. It has very low activation energies. What that means is you basically don't have to be concerned about kinetics. When we have talked about equilibrium before, it's like, well, this is the favored state, or the K is greater than 1, so you should form products, but it's really slow. Acid-base reactions are super fast. They are so fast, you don't have to be concerned about kinetics. You can just care about what is the equilibrium, right? What's the equilibrium constant? What's the favored equilibrium? And then boom, that's it. So what that means is if you know something can behave as an acid or as a base, it will do that chemistry. If you pair it with either a base or an acid or whatever it needs to be paired with to do those neutralization reactions. So you can look at chemical structures, you can look at chemical formulas, you can predict chemical properties, and you can use that to your advantage. So there's a lot of cases where we use the fact that something is an acid or a base to affect what it does, to affect its properties, to drive it, to change it, to modify chemicals, and to make them do the changes we want them to do. And this is extremely common in pharmaceuticals. So pseudoephedrine C10H15ON. This molecule, the 3D structure is shown in the bottom left there. That's a nasal decongestant. So if you get it inside a human's nose, they can, you can clear up, say, sinus pressure, those sorts of things. So this has good or desirable properties as a medicine, but it's got some problems. One, it's mostly nonpolar. Okay, so you can look, there is an oxygen and there is a nitrogen in the chemical formula, but there's also a lot of carbon and a lot of hydrogen. This thing can form hydrogen bonds, there's an OH, but not a lot of them. And when you have most of this molecule, it's mostly just dispersion interactions, pretty weak interactions. So it's not very soluble in water, which is not good because humans are mostly water. So it's not really dissolving into humans. It has really weak intermolecular forces, which means it has, really low melting points, similar to the low boiling points we've talked about previously for weak intermolecular forces. It smells, has a high vapor pressure, so it smells really strongly and doesn't smell very good. And it's also really reactive, right? When you start to get, these sort of kind of softer materials, the molecules are able to move a bit more. They're not as locked into place. And all of those things lead to a really short shelf life. If you put this molecule in the medicine cabinet, people would notice it, people wouldn't want it in their medicine cabinet, and it would react, it would go bad really quickly. But this thing has a nitrogen in it, and that's the blue molecule in the structure right here. And that nitrogen has a lone pair on it, which means this molecule is a base. A lot of medicines, a lot of pharmaceuticals contain nitrogen atoms in them, so almost all of them are bases. So the N can act as a base. You react it with, say, an acid, so you can pair it with an acid. That now creates the conjugate acid of pseudoephedrine, so C10H15ONH+. Now you have formed an ionic compound, because this is a cation. It's a very complicated polyatomic cation plus chloride. So the solubility rules are no longer based around being polar or nonpolar. It's based around the ionic solubility rules, and chlorides are almost always soluble. So this thing is now highly soluble in water. Because it's ionic, ionic compounds have really high melting points and high stability. You have solved all of the problems. Importantly, this is not always necessarily true, but importantly, this cation still behaves as a nasal decongestant. So it still has all the medicinal properties, but you've basically taken care of all the bad physical properties that would have made it not a useful medicine or not something that people would want to or really could use on a large commercial scale. And so you've solved for all those. So this drug is sold as pseudoephedrine HCl. It's the active ingredient in Sudafed. This is a very high use product. And so it's sold as pseudoephedrine HCl, reflecting the fact that HCl is used in it. A lot of times you'll hear like, oh my God, it has HCl in it, but really it's reacted. Yes, you did put a very potent acid into it, combine it with it, but it's fully reactive. The HCl is fully neutralized. The companies wouldn't waste HCl putting extra in there. And so you have this full, kind of new compound that's an ionic compound that has all the properties, because pseudoephedrine was what had the bad properties. You now have this new ionic compound that still has the nasal decongestant, but much more preferable in terms of all of these sorts of physical stability and kind of shelf life properties. So again, that's why we care about acids and bases. It allows us to predict what pseudoephedrine can do. And it's a small change. That's one of the important things, that using an acid, it leads to a really small change. You just add this H, which is why the actual, most of the chemical properties don't really change. It just has an extra hydrogen on it, H+, and so it still can do all the same chemistry inside your nose.
Okay, another participation question. We're also halfway through the set of videos, so gotta get to the back half, maybe find some more questions there. See ya.